Thank you, Ellie, and thank you for that introduction. And welcome to everyone joining us for this session. This is Getting Ready to Teach, or Welcome to Pearson for International Advanced Level Physics. And we'll be looking at the specification, the content, and forms of assessment over the next couple of sessions this morning and tomorrow. As I say, my name is Keith Penn. I've been a teacher of physics to A level for 33 years in schools around London and East Anglia in the UK, and I'm joining this call today from just outside Cambridge, where it's a slightly nicer morning, a bit more mild, and the rain has stopped briefly, which is great. And I hope you're having a good day where you are. There will be some people, I recognise some names. Over the last 2 days, Monday and Tuesday this week, I did a presentation of Getting Ready to Teach on international GCSE physics. And clearly there are some people for whom they'll have moved school or moved to a school which is offering both those specifications, the IGCSE in physics and also the international advanced level. So there's some people on the call who will already have followed the training for international GCSE, and I have to open with a kind of apology to you because you'll see there are some similarities. Obviously the content and the level of difficulty is very different in the international advanced level, but the structure of the course, the layout of the specification, and therefore the structure of this presentation does have some similarities. We go through the same sort of pattern. Oh, it appears that my screen's not sharing. I'm so sorry. I thought I had done that and I hadn't. How's that? I think that's sharing. There we go. Apologies for that. Sorry, those similarities actually provide some reassurance for students. There's some reassurance and advantage to students because if they're following the specification, the Pearson Edexcel specification for international GCSE and go on to do the international advanced level, they will see similarities in terms of the layout, the course structure, the rationale behind the examination, and that provides some security, as it were, and some familiarity, which can only be helpful. As we all know, physics, both at GCSE and especially at advanced level, is a hard subject. It's challenging for students and a real achievement when they achieve a good grade at the end of it. And it's beholden on us to make the rest of it as simple as possible, really. So having this familiarity with a sort of common thread, a common layout between GCSE and advanced level, we think is helpful. But as I say, for those of you who are doing both of these courses this week, you will have some repeats, as it were, and I apologise for that. So in this training, we're going to identify how the qualification is devised, to review the content of the qualification, to explore how to plan the course and planning lessons, and then in more detail in tomorrow's session, we will be understanding the assessment of the qualification and how to prepare students for those assessments, and a little bit about the support that's available from Pearson. I will close off my camera for the moment and move on to the rest of the presentation. Starting with a welcome to Pearson. We're the world's leading learning company, and as the UK's largest awarding organisation, best placed, we believe, to provide qualifications aligned to the British educational system. Our international heritage stretches back over 150 years, and today we partner with schools, universities and employers worldwide, offering world-class, globally recognised qualifications to over 3.5 million students a year. Pearson Edexcel is trusted and recognised qualifications partner to 6,500 schools, colleges and employers globally. We mark over 10 million exam scripts on behalf of the UK Department for Education each year, and we operate in 70 countries worldwide. R10, the documents link should be down at the bottom of your screen. Oh, there we go, at the bottom of your screen. Thank you, Ellie. Starting with an overview of the specification. This just outlines the main starting points, along with the Getting Started guide, resources for the specification, and what's to be found in them. The specification is the main document that you need to teach the course. It outlines the aims of the course, the content that you must cover, and all the information you need about assessing your students. A copy of this document is in your download pack and in the website. And I'll show you links to the website later on. There are also sample assessment materials, and the sample assessment material document provides examples of the question papers, and it's especially useful when it's a new specification. But now that we've had several series of live exam papers, it's arguable that the real papers, there have been several years of that now, have become a more important resource than sample assessment materials. So increasingly, when you're using past paper questions, you're using past papers as opposed to the sample assessment materials. Sorry, I couldn't hear that. So I wasn't able to hear that.
I'm set. مش عارفة تمشي كمين مش لاقي الشي بتاعي.
Okay, sorry, moving on. Structure. The International Advanced Subsidiary and Advanced Level in Physics are modular qualifications. The content is relevant for learners who've achieved a GCSE or an international GCSE in physics and who want to continue to study this subject at a higher level. The assessment consists of 3 written papers at IAS level that are externally assessed. The international advanced level consists of 3 further written papers that are also externally assessed. The AS can be claimed on completion of the international advanced subsidiary units, the IAS units, and the full advanced level can be claimed on completion of all the units, the IAS and the IA2 units. The content covers major topics, including mechanics, materials, waves, electricity, fields, thermodynamics, radiation, particles, oscillations, and cosmology. The specification also includes 16 core practical activities. This is the minimum number of practical activities that learners will carry out. Centres are encouraged to enable learners to carry out additional practical activities to further develop practical skills. Learners will develop their knowledge and understanding of physics by applying the concepts in the specification to a range of different problems that include a variety of contexts. Problems will require the application of mathematical skills. Learners will also develop their practical skills. The compulsory content section gives an indication both of what needs to be taught and the level to which it needs to be taught. As it says here, as a minimum, all the items in the content must be taught. The word including in the content specifies the detail of what must be covered. The sentence on assessments is important. It means that questions can and will be asked, which are set in a context different to that in which the knowledge and understanding was first learned. Students need to develop the confidence to be able to apply their learning to different unfamiliar contexts. Hence the comment here about a good range of examples. It would not be possible to predict or prepare students for every possible context which examiners might come up with. The key is to expose students to a wide enough range of opportunities to realise that they can successfully apply what they know and what they understand in other contexts. So as it says in assessments, use a range of material and are not limited to the examples given. Teachers should deliver these qualifications using a good range of examples to support the assessment of the content. And the depth and breadth of content, teachers should use the full range of content and all the assessment objectives given in the subject content section. This is a page from the content section in 1.4 materials, indicating how the core practicals are shown. You can see, if I highlight with an arrow, that the core practicals are identified in bold in this specification. There'll be more on the assessment of practical skills later on in the presentation. One down here too. The slide also shows how the specification content pages give more information. For example, identifying which formulae need to be able to be used rather than remembered. So you can see on this page, there's core practical 2, use a falling ball method to determine the viscosity of a liquid, and core practical 3, determine the Young modulus of material. This summary from the specification of the unit breakdown in both the IAS and the IA level qualifications. The slide also shows how the specification content pages give more information, for example, identifying which formulae need to be able to be used rather than just remembered. So the IAS, the qualification, consists of 3 externally examined units. It's the first half of the full A level and consists of 3 units, 1, 2 and 3. It can be awarded as a discrete qualification, or it can contribute 50% towards the full A level, and the majority of students do go on to do the full advanced level, but a significant number stop at the end of the AS. The qualification will include questions that target maths at level 2 or above, and overall a minimum of 40% of the marks across the papers will be awarded for mathematics at level 2 or above. So as you'd expect in an advanced physics course, there is a large mathematical content. For the international advanced level on the right of the screen, qualification consists of 6 externally examined units. The international A level consists of the 3 IAS units, 1, 2 and 3, and then the 3 follow-up IA2 units, 4, 5 and 6. So students wishing to take the advanced level must therefore complete all 6 units. It also includes questions that target maths at level 2 or above, and as in the AS, a minimum of 40% of the marks will be awarded for maths at level 2 or above. This is an overview of the 3 units in the IAS and their assessment. Externally assessed, Unit 1 and Unit 2, well, all 3 of them are externally assessed. Unit 1 and Unit 2, the content modules in this part, have a written exam of 1 hour 30 minutes duration, and each are worth 80 marks, which is 40% of the IAS each, or 20% of the full A level. In both cases, these papers may include multiple choice, short open, open response, calculations, and extended writing questions. And it does say in that part of the specification, students will be expected to apply their knowledge and understanding of content and practical skills to familiar and unfamiliar situations. Unit 3 is slightly different. That's where the practical skills in physics are assessed. It's entirely a written exam, but it's assessing the students' learning of experimental procedures and techniques that they've developed while studying Units 1 and 2. So it's a slightly shorter exam, 1 hour 20 minutes, is amount for 50 marks, accounts for 50 marks, and that's 20% of the AS or 10% of the full advanced level. The paper may also include short open, open response, calculations, and extended writing questions. You'll notice there are no multiple choice questions in Unit 3 paper. And there's a similar pattern for the IA2 modules, the 3 modules which make it up to the full A level. Unit 4 and Unit 5 are once again the content modules, as it were, and Unit 6 is the unit where the practical skills which have been developed in Unit 4 and 5 are assessed. So the exams for Unit 4 and 5, they're all externally assessed. 4 and 5 have written exams of 1 hour 45 minutes length, each accounting for 90 marks, which is again 40% of the IA2, 20% of the full advanced level. And as before, these papers may include multiple choice, short open, open response, calculations, and extended writing questions. When we look in more depth at assessment in tomorrow's session, we'll be going through examples of those sorts of questions and how they're marked. Unit 6 exam is slightly different again. It reflects Unit 3, so it's assessing students' learning of experimental procedures and techniques that they developed through Units 4 and 5. It's a slightly shorter written exam again, 1 hour, 20 minutes, and it accounts for 50 marks, 20% of the IA2 or 10% of the full A level. You can't, of course, sit the IA2 as a separate qualification. The IAS is possible as a separate qualification, but the IA2 modules can only be used as part of a full advanced level. As before, this paper includes all the types of questions we've listed, except for multiple choice. No multiple choice questions in the Unit 3 or Unit 6 papers. Okay, this is part of a question from one of those papers. And all I'm asking you to see is have a look in your specification and to identify which specification point you think is being assessed by this question. You don't have to put feedback in the chat. I just want you to have a look through the specification and see if you can find where you think which specification point is being assessed. One of the points I'm making, I guess, with this activity is that any question in an exam will assess specification points, parts from the specification. People writing the setting the question papers, writing the exam papers, only look at the specification for setting those questions. Sometimes people will say, oh, we used the Pearson textbook and there was this item in the textbook and it never came up in the questions. That's because the examiners do not look at textbooks or any other materials when they're writing the papers. They only refer to the specification. So your go-to place for seeing whether something's likely to be in the exam or not, and what level it's likely to be in the exam, is the specification and that alone. So every question will be linked to a specification point or one or more specification points. And the answer is topic 1.4, materials, in Unit 1, and it's specification point 30. So thank you to those who've stuck that in the chat. Thank you. So it's specification point 30, which says, be able to draw and interpret tensile or compressive stress strain graphs and understand the term breaking stress. And that's exactly what's happening here. Okay, so you're expected to understand the stress strain graph that's being shown there for Kevlar and steel and nylon, and use that to explain two advantages of using Kevlar in cables compared to using nylon. It's worth just making the point here that when a question includes a graph like this, then it's expecting students to refer to that graph in their explanation. They're not just expected to explain those advantages using their other knowledge of those materials. They will need to get full marks to refer to the graph itself. So if there's a graph in the question, it's not there just to illustrate, it really is something they're expected to use in their answer. So here's a content overview, simply an opportunity for you to get an idea of topic coverage within the whole specification. And you might just want to spend a moment considering what's been included and what's being left out compared to any other courses you might have taught previously. It would be absolutely impossible for any advanced level course, or any physics course for that matter, to cover every single field of physics. Decisions have to be made to leave some things out and to include some things. So different specifications will differ in their content. It would be unusual, more than unusual, to see some things completely left out. You'd expect it would be a strange physics course that didn't include anything on mechanics, for example, anything on electricity, anything on waves. But there are things which where there are choices to be made, and the decisions being made to look at a smaller number of areas in advanced level depth, rather than to try and cover lots and lots of levels at a much more surface, lots and lots of material at a much more surface level. So the choices are made so that the students experience going in some depth into key areas of physics. So you can see as the titles of the units themselves kind of give it away. So Unit 1 is mechanics and materials. Unit 2 includes waves and particle nature of light, the wave-particle duality, electric circuits. Unit 4 includes further mechanics, electric and magnetic fields, nuclear and particle physics. And Unit 5 includes thermodynamics, nuclear decay, oscillations, which obviously has a link with the waves in earlier Unit 2, and astrophysics and cosmology. just want to give you an opportunity to choose one of the topics or part of the topic and say what order you think you would teach that topic. Where would you start? Which part of the topic would you go on to? Which order would you teach the elements of one of the topics? So you can choose any topic you like in the specification you have and just say, you don't have to write out full lesson plans, just literally what area would you start with? What would you go on to? Why would you do it that way around? I'll stay quiet for a couple of minutes while people put their ideas into the chat. So thank you, Imad. Start with properties of materials, then up first, then go on to viscosity. Okay, fair enough. Good. Oh yeah, solid properties. Yeah. Do you mean you have a question to ask us, Osama? Okay, thank you for contributions, Son. I apologise if I cut you off in mid activity, but obviously I want to move on with it. Those of you who already did the introduction to IGCSE on Monday and Tuesday this week will be ahead of people in this sense, because the principle is the same really, because basically the point I'm making is there isn't a single right order to teach the topics. What I don't want you to think is that the order in which the topics are laid out in the specification is the recommended teaching order. Sometimes there's a logic to the way in which they're laid out in the specification. Well, there is a logic to it, but you don't have to teach them in that order. You have some free choice, and very often that depends on knowing the students you've got and what their prior learning is. If you taught them for their GCSE, you'll have an idea about their prior understanding, but I think it's always good to start in a topic with where students currently are and build from that. So I think somebody said that within, yes, Omnia said mechanics, as they're familiar with it from their GCSE. And it's often worth starting with what students already know and move on and build in the complexity. Clearly, there are some parts of topics that have to follow other ones because the learning builds one part on another. But many of the topics you can start in different places, and there won't be a single right answer to that. That will depend on you and your students, and what's right one year might not be right with your same teacher the following year. Okay, so I'm trying to open up consideration of the idea that you need to consider which is the most effective and logical way to present a topic. It isn't necessarily the way it appears in the specification, nor the way it appears in the textbook that you might be using. You do have to make a decision about it, what's best for your students. So thank you for those. I'll look at some other examples that have come in here. Momentum starting with force, then elastic and inelastic collisions. Yeah, that makes good sense. So there are some concepts within force that have to come early on because other ones build on those. Electric current, start with basics like charge, time, and set the foundations, and after that move on to other concepts. Yeah, and I think there's good sense starting with relatively simple material and move towards the more complex and building students' confidence as they build their knowledge. Imtiaz has said nuclear structure, radioactivity, then nuclear reactions, fundamental particles, radiation detection, universe and cosmology. Yeah, good logical sense. As I say, it will depend from time to time on what your students already know or what they've remembered from their prior learning. Resolving vectors before adding force and moments. Yeah, good sense. Thank you for those. The point I'm making really is it's a decision to make and not necessarily a decision you can make once and for all. You'll need to consider the students in front of you and what will be the best order for them. Let's move on to look a little at core practical skills. In order to prepare students for the assessment of experimental skills, centres should give students opportunities to plan experiments, implement their plans, collect data, analyse their data, and draw conclusions. Experiments should cover a range of different topic areas and require the use of a variety of practical techniques. People often wonder what the difference is between GCSE and advanced level. It's not just that the material is harder. There's also a difference in what we're expecting of students. And students are expected to be much more independent learners at advanced level than they might have been at GCSE. It's no longer possible really at advanced level simply to deliver it all as lectures and students simply make notes and absorb it all like sponges. There has to be some independent thinking, and the more opportunity for students planning their own experiments, discussing their ideas, sharing ideas, talking around the ideas, the much better they will be able to perform in the exam. It really does need to build in quite a lot of independent learning techniques that aren't always present at GCSE. I mean, there can be good independent learning practices developed at GCSE, and that's always good preparation for later. But at A-level, I would say it's absolutely required that students are expected to learn for themselves to some extent and be able to think for themselves. And that includes planning experiments and being able to implement their plans and being able to discuss why they made the decisions they did. How do the core practicals cover the practical skills? As long as you follow the programme of the 16 core practicals, you'll automatically cover all of the standard techniques and apparatus that students are expected to know and reproduce in their examinations. However, and this regularly comes up from examiner reports, the students who do best in units 3 and 6 are often those that have carried out a range of practicals. So you should really aim to complete more than just the core practicals. Students really do get familiar, not just with the equipment, but with the ideas when they're able to demonstrate that they've done the practicals themselves, and done practical work, and familiarity with particularly things like electrical circuits, forces, setups, and so on. Here's an extract from the Teacher Practical Guide, an invaluable resource. You can download it with the online training, or you can get it directly from the Pearson website on the International Advanced Level Physics page. Core practicals are part of the specification, and the students are expected to know them for the examinations. Students can use different methods and techniques to those stated, but they will still need to know and understand the methods that are stated in the core practicals. It's strongly recommended that you do other practical work as well as the specified core practicals. They need not include expensive pieces of apparatus. Any practical work that your students attempt, not just the core practicals, will develop their competency. As you might guess from the title of this guide, Practical Guide Teacher, there's also a Practical Guide Student. The content is almost exactly the same, but the teacher guide includes answers to the questions set within the student's practical guide. So both are downloadable freely, and you can print them off or use them as PDF files. So, teaching practical skills. These are collated summary comments from the examiner's reports on exams for contents units 1 and 2. Okay, what our examiners have noticed in units 1 and 2, many candidates showed a good progression from GCSE to A-level, with prior knowledge extended and new concepts taught and understood well. Candidates found the length of some of the calculations, longer than they are obviously in GCSE, found the length of some of the calculations to be challenging, often missing out key steps, and therefore only scoring 1 or 2 marks for interim steps. The new regions of the specification were answered as expected, if not better, which is good news. It was the problem-solving nature of some of the questions, as well as the requirement for explanations in an unstructured setting, that many found to be challenging. It's true to say across the board that students, particularly physics students, find it more challenging to tackle questions where they're expected to do some free writing, in other words, where there's a big area of blank page that they have to structure their essay, than they do to answer questions which are broken down into much shorter sub-answers. And they find it easier also to tackle calculations than they do to tackle written questions. The main challenges were on questions requiring more application. Candidates who had a sound understanding of the physics involved did not always demonstrate this in their responses due to a lack of precision in the language and terminology used. Some missed exactly what the question was actually asking. While the mathematical ability seen was strong, application to the context was not as expected. And a little bit of feedback from Unit 3, which is where they're tested on experimental learning, practical skills. For this paper, the topics included materials, waves, and particle nature of light. As understanding of the core practicals is assessed by the Unit 1 and 2 papers, the practical context met in the Unit 3 paper may be less familiar. However, it's the skills rather than the details of the practical that we are assessing. There were many questions that would be familiar for candidates, but there are some questions where performances would suggest they were unfamiliar with the practical skills. Understanding of keywords such as resolution and command words such as describe how proved a challenge to candidates at the lower end of the ability range. So sometimes students showed by the way in which they answered questions that they didn't fully understand what the command words were asking, so they answered not quite the question which had been asked. At all ability levels, there were some questions where candidates answered in generic terms rather than being specific to the particular practical described in the question. I just want to give you an opportunity to say, what do you think are the implications for teaching and learning which arise from the feedback from the examiners' reports that we've just been seeing? Do you think there are any things we should consider in our teaching and learning to pick up on what examiners are saying students are finding difficult? I'll give you a moment or two to make any comments you might wish to in the chat. I'll just flip back through the last 3 slides just so you can remind yourself of what those points are. So I'll just spend a couple of moments on each slide again to see what those points were. So candidates found the length of some of the calculations to be challenging. It's one point to be raised. Students found problem-solving questions more challenging and writing longer explanations in an unstructured setting. And candidates who showed that they knew the physics, didn't always demonstrate it in their responses because of the precision of language and terminology that they used, and some missed exactly what the question was asking. And in the practical area, well, I guess the answer to this part, the implication of this is straightforward. There are some questions where performances would suggest they were unfamiliar with the practical skills, so that we need to ensure that students are as familiar as we can make them with the practicals. Okay, Salma, make sure students are familiar with the 3rd tier vocabulary from the topic. Yeah, absolutely. They need to be aware of the technical vocabulary, the correct use of scientific terminology, and also how to express themselves clearly. And I have to say, in my experience, students will not be able to express themselves clearly in written form unless they can do so using the spoken word. So the more opportunity we give students to talk about their learning, to describe their explanations, describe their experiments that they've done, describe their reasoning to other people, other students, once they can do that verbally, they'll be able to do it more in writing. I think we have to build in opportunities for students to talk about their work as well as then to write those answers down. especially for learners for whom English is an additional language. Correct use or identification of command words. You can download a list or a poster of the command words from the specification. And the more, I mean, I've seen many labs where usefully they put up all the command words around the lab with their definitions so that students can refer to what the command words mean. But as you'll know yourself, anything you post on the wall of the lab before very long becomes just like wallpaper and students stop noticing it. So it's at least as important that we as teachers constantly use those command words in their real context. So we might ask students a question which includes the word explain. And if a student gives you an answer which is a describe answer, acknowledge the answer, say, yes, that's good, but you've only described it. To explain it, you need to tell me why that's happened, include because in your answer. If we use the command words as teachers, as they're intended throughout the course, students will become familiar with what they mean. More peer instruction, absolutely. Students talking one to each other, particularly at advanced level, is really, really powerful. And that's how they will when one student explains work to another, both of them benefit from that. The one who's being explained to, but the person doing the explaining learns at least as much from that, because putting it into words solidifies and embeds that sort of learning. You know, it never becomes a completely firm concept in their mind until they explain it to someone else. Misunderstanding of concepts, failure to interpret questions, inadequate practical skills. Yeah, absolutely. And they do need to use the vocabulary and the scientific terminology that's within the specification. They need to use keywords such as resolution in the way in which they're defined within the specification. Model the longer calculations and show students the answers in their entirety. Yeah, that's good. And also good, I think, is we will all have lessons where we set students a number of calculation questions. You know, students will sit there and work through some examples of calculation questions. Really powerful part of that can be to get a student to come up after they've done several questions and go through their answer on the whiteboard or whatever, so other students can see their structured answer. The student doing the presentation benefits enormously from this because it really embeds the fact they have to lay it out in logical sequential steps. You might get away with it being all over the page when you're just doing it for yourself, but as soon as you're explaining the reasoning, how you got to this answer to other students, it has to be laid out in a logical way, otherwise other students can't follow it. And so it gets students into good habits of listing all the steps, showing their working, starting with the equation, substitution, rearrangement, you know, and showing those steps one after the other. So getting students to model their calculations for others is really powerful too. It also frees you as teacher to be one of the observers, so you don't have to go through the question yourself. You're sitting there being able to comment on how other students have gone through it. So really, really powerful part of doing calculations is to get students to show others their reasoning. And obviously you can allocate questions to different students, so everyone in the group has an opportunity to present some of their own work to others. They're quite nervous about it to start with. You have to build a positive learning environment where students know that if they make a mistake, they're not going to be ridiculed, but the mistake is an opportunity for learning. So you've got to spend some time building a safe learning environment where students know they can think out loud and make mistakes without being ridiculed by you or by the rest of the class. But once you've built that safe learning environment, it's a really, really powerful tool. And getting students to mark exemplar answers is a really, really powerful activity. So yes, thank you very much for those. Okay, let's move on. Content overview. How do I make sure I cover all the content? There are several resources, all downloadable from the IAL website, physics website. There's the course planner, scheme of work, getting started guides. You have to consider the specification, of course, lesson plans, schemes of work, and year planners. It's really frustrating to get to the end of the 5th term and realise you've still got a quarter of the course to go through. So planning how much you will cover and a sort of calendar of events is really important, particularly when you're picking up a new specification. It's really easy to get carried away and covering the early topics in too much depth that you don't leave yourself enough time to go through the later topics. And as you expect, some of the later topics will often be more complex and perhaps need more, not less concentration. In addition to the specification, there are other resources freely available on the website to help teachers plan their scheme of work. All of the documents, as I said, are freely downloadable online from the Pearson website, and the course plan and the scheme of work can provide a useful starting point for matching the programme of delivery to the time that's available within your school or centre. Each school or centre has its own peculiar allocations of time, how much time you get per lesson, how many lessons per week, and so on. And it's easy to use these sort of course planners and scheme of work to adjust to the timing that you have available. So here's a screenshot of the first part of the scheme of work model. The model scheme of work gives one way of approaching the content so that it's all covered during the time available. Remember, you'll need to adjust the time to fit your own timetable and the number of contact hours you have per week, and also the time period over which your school delivers the whole course. Rider that I mentioned earlier, the order of topics in the specification and in this course planner are not intended to suggest that this is the only order in which to deliver the content, but because they're presented as Word documents, so they're editable, it's fairly easy to cut and paste and arrange them into the order that you want to teach. It does give here quite a useful layout, and you can see in this scheme of work, it lists the weeks, what prior learning is expected, then the basic content of the lessons, and teaching suggestions, some activities that might take place within a lesson where you're delivering that content, and the specification reference areas on the right hand side. Yeah. Okay. How do you plan your lessons in physics? Do you have a common lesson structure as a starting point? Are there any ways you might need to adapt your method of lesson planning to deliver this specification? Some schools have the department will set the sort of lesson plan performer. Some schools, the school will have a set performer and all lesson plans have to fit into that. In other places, you start with a blank sheet of paper. I wonder if you could put in the chat room how you plan your lessons in physics. Yeah, many departments increasingly provide a template, and that can be useful, particularly if you're doing some team planning. If you're lucky enough to be in a large centre where several teachers are delivering the same specification at the same level, then it can be, you can do some common planning and co-planning and share those plans and schemes, and that allows you to come back in department meetings and feedback on what worked and what didn't work so well. So a common lesson structure can really help with that. The start of the topic starts with required knowledge, and lessons themselves usually start with recall questions, open discussions, and more recently we're moving to workbooks. Yes, I think a number of schools. Yes, I meant to ask about how students store their work, because many use loose leaf folders, some use exercise books like they might have used lower down the school. It's worth saying, if you've got a preferred way in which you want students to record their work, it's worth sharing that with the students themselves. Because if they just start off the way they have gone in GCSE and get to the end of the first time and realise that wasn't the most effective way to do it, it's quite hard to go back over it and correct it. Whereas if you give some guidance early on, students can get into a good plan of organising their work. Recording what is learned in theory lessons is relatively straightforward, but how do you insert practical learning within that? Do you do it chronologically when you did that practical, or are they all kept together in a separate practical workbook? All of these are possibilities, but it's worth having that discussion. Otherwise, the notes students are making don't become an effective part of their revision resource and learning resource later on. Start with a real life example, just in time teaching, peer instruction, open-ended questions, instruction modeling. Great, great. There's some really good plans, and this is an opportunity just to sort of share some of those. The point I'm making really is it's something you can develop in your own style. You don't simply need to follow the textbook that you're using. In fact, there are many reasons why not just following the textbook will improve the effectiveness of students' experience and learning, and being able to inject some variety into there so students don't know exactly what each lesson is going to be. It's useful to have some common structure so students have some confidence, but to be able to inject some surprises as well is really helpful. Think, pair, share, I think is excellent. And I think too often we don't allow enough time for students to think. We tend to think we abhor silencers. So we'll ask a question and then jump in too quickly with the next tip or the next answer. And particularly at advanced level, I think we often need to give students more thinking time, and not to be embarrassed by those silencers, but to recognise that students will need to spend some time thinking of the answer to a question, and even perhaps contribute just part of the answer, and several other students can jump in and add to that answer. So the idea of developing sort of group learning can be really effective. Okay, let's move on to look briefly at support and the types of support that are available. I'm going to mention briefly teaching and learning materials, past paper, mark schemes, examiners' reports, teacher resource packs, all available online, and published resources, student books and lab books. I mentioned several times the website, and here's the home page of the International Advanced Level Physics. You can follow a direct link to it, which is qualifications.pearson.com/home, but it's probably easier just to use a good search engine like Google, but others are available, and type in the words International Advanced Level Physics and Pearson or Edexcel, and it will, any combination of those words will take you to this page or a link to this page. And you can see the page itself is full of hyperlinks to other pages behind it. So if I draw your attention to the kind of blue panel halfway down the right-hand side where it says course materials, each of those lines underneath there in blue is itself a hyperlink to its own set of pages. Specification and sample assessments are those two documents on that page. The exam materials, you can see an enormous number, 236 past papers, because that includes all the past papers available from each of the series that have happened in this, the mark schemes and the examiner reports, all within those exam materials. And the teaching and learning materials, you see 34 of those. When you click on that, things like books on specific parts of the topic, teaching resources, and things like the schemes of work and the course planners and things like that we mentioned earlier. Just to mention about the exam materials, whilst I'm thinking about that, when you click on the exam materials, you'll see that the most recent ones, the ones that happened in the last series, will have a padlock symbol next to them, like a little grey padlock. And that means they're locked. You can't enter them without a username and a password. The purpose for that is requests from schools themselves. Many schools use the most recent papers as the mock exams for the current cohort of students. And the last thing you want is, if you're doing that, is for students simply to go online, search the mark scheme and learn the answers off by heart before doing the mock exam. It doesn't help anyone. So they're padlock locked. That doesn't mean you can't access them. As a teacher within a school delivering Edexcel qualifications, you do have a right to access those. And the way you do that is to talk to the exams officer in your school. The person in your school who enters students for exams and coordinates all the exams has access to all the materials that they're entitled to, including those padlocked papers. And crucially, they also have the ability to create for you a username and a password so that you can access those materials. So don't be put off by materials which look as though they're padlocked. That's simply to stop someone Googling them and just opening all the most recent mark schemes. But you have access to them. Talk to your exams officer and they can give you a username and a password to get into there. Exemplar materials are marked exemplars, examples of real student attempts at the past paper questions with commentaries from the examiners on how they were marked, what went well, what didn't go so well, and the reasons for giving those marks. We'll talk more about using these exemplars when we look more through assessment in tomorrow's session, but they come in the examiner reports after each series of exams, but they're also collated together in booklets like this with some common exemplars and really useful learning materials for teachers like ourselves, for departments to work together on how the mark scheme works, and also for work with students. And we'll discuss those a bit more tomorrow. And they're available both at advanced subsidiary level and the full A level. The Getting Started guide just provides an overview of the international advanced level. It gives information about the content and assessment, much of the stuff we've been going through in this session, and hopefully gives you a better understanding of what this means for you and your students. It's useful if, like I assume you are signing on to this course, if you're new to the specification, either because you've moved to a school which teaches this specification and it's not the specification you taught previously, or your school has changed to Edexcel from a different exam board, or if you're new to teaching. For all those reasons, both this course but also the Getting Started guide can be really useful because it gives you an overview of the things you need to know when you first start off. Teacher mathematics support. I'll quote a little bit from this support to explain what this is about. Many A-level physics students find mathematical concepts difficult, not only those who are not also taking maths at A-level. We have also all had our patience tested by capable students saying physics is just maths or all about equations. These students become adept at putting numbers into selected formulae correctly for a GCSE without necessarily having developed the type of mathematical reasoning that's needed for more advanced physics. Both these groups of students find the transition to A-level difficult. The new specifications raise the bar further by demanding that 40% of marks be for level 2 maths, moving away from questions where students put the numbers into a formula and towards problem solving, where students have more responsibility for selecting both the correct data and the approach to finding the solution. Part of the reason for students' difficulty is that physicists and mathematicians have different relationships with maths, and so students learning in maths doesn't always transfer well to our laboratories. For a physicist, the maths describes a picture, a representation of a relationship describing a physical reality. For students, maths is an absolute that gives you the answer when you put the numbers in. Every opportunity should be taken to relate mathematical ideas to real physical situations, if possible in a practical way, as well as creating explicit links to where the same skills are used in the other sciences. So I do recommend this booklet. It's not just teaching you maths, it's saying how maths is specifically used in the advanced level physics. Yeah, Mohammed's made the comment, there's a gap between the content level in textbook and past paper questions. As an easy example, moments is very basic level in the textbook, but questions in the paper are not. And you're absolutely right. It's why I recommend teachers using things like Exam Wizard to use real past paper questions as often as possible, not just for mock exams and things like that, but also for regular homework so that students get used to answering the type of questions that are set in physics. And there are projects like the Isaac Physics, for example, project, which push it that extra stage further and give some really high level. So for more able students, well worth having a look at projects like that produce some more difficult, more challenging questions to get students to really think. And Obaid has suggested there Hodder Physics for developing students. As I said, the Isaac project is really good, obviously named after Isaac Newton. It's done by a group of people at Cambridge University, but again, produces some questions that make you think, more challenging questions where students need stretching so that when they get to the exam itself, they have the confidence to be able to tackle those more challenging questions. You're absolutely right. Textbooks sometimes focus on questions which are rather easy to link. Can I provide the link? I will have a quick go at that. I'm not sure whether I can or not. Give me a moment. It doesn't seem to be letting me print links in, but I'll just give it a go. Let me have a go. Here we go. How's that? Yeah, there we go. Okay, it did work for that. Okay, I'm not on the board of Isaac Physics, so I'm not selling something there. I've just found it really useful, so it is well worth having a look at. Teacher Practical Guide. Mentioned this earlier on. The guide is designed to support you and your students through all elements of practical work in the IAS and A-level specifications. Can't recommend this guide highly enough. It tells you how to do the practicals, but also really important information, things like questions to support learning, higher level thinking skill questions, which get students thinking not just about what we're doing in this practical, but why am I using this technique? What am I trying to find out? What's the science that's happening behind it? Really push those more evaluative learning points from the practical. So focusing on what are we learning in this practical, not just what are we doing. I find Exam Wizard amazing, but when I want to export the worksheet to PDF, sometimes error appears in downloading. I haven't found that. It's worth emailing the science advisor and explaining the error that you're getting, because they might be able to support you in what the issue is there. I've found the transfer to PDF has been okay when I've used it, but it may be the particular software that you're using, you know, I don't know whether you're working on a Apple machine or a Windows machine and so on, and I don't know whether it's different with different platforms and so on. It's worth talking through with them. There are teams who will support you on that, so I would contact the science support advisor first of all, Irene, who I mentioned, or Mark, and but they will be able to put you in touch with the people who can support you on that. Scheme of work, mentioned earlier. Scheme of work is broken up into units and topics, so there's a greater flexibility for moving topics around to meet planning needs. It includes recommended teaching time for topics, though of course this is adaptable according to individual teaching needs, classroom activities, teaching points and suggested teaching resources, objectives for students at the end of the topic area, and examples of integrated transferable skills. So again, a useful resource, very good resource, especially if you're starting with new specification. And of course, published resources, as you'd expect. As a publisher, Pearson produce student books and teacher guides for all of the specifications that they deliver, that they offer, sorry. So you can see here, the Physics Student Book 1 and Student Book 2. I'm getting some crosstalk actually. Check that your computer is muted, otherwise we're getting some crosstalk, I think. Sorry. Yeah, and if you buy these books, the paper books have within them a code which allows students to access the digital versions too, which is not just the content of the book in digital form, but also some additional resources, interactive questions, links to videos, other links to useful resources. So the book also gives link to more digital resources that are available. The whole, if you if you Google or search the publishing department of Pearson, you can see the full catalogue of what resources are available for your subject. Although we believe these are very good textbooks, I must give the rider that I've given over recent days, and they are matched to the specification in both content and level. Remember, it's not essential to use Pearson textbooks to deliver a Pearson specification. If you transferred from another specification and you've got textbooks that you're really fond of and that you think deliver the physics really well, there's absolutely no reason why you have to chuck them all in a skip and start again. You can use the resources. It's your responsibility to check that they're covering the same content, or the chapters you're using covering the same content and to the correct level. But there's absolutely no reason why you have to ditch good textbooks in order to buy new ones because you're delivering a new specification. Just as I say, check that you're covering the same work. And Pearson have also published a lab book that covers all of the core practicals. It contains instructions for each core practical, together with some questions to ask. Students can enter their results and observations directly into the book, And some schools have reported that they find that cheaper than photocopying the material to produce all of those. So have a look and see whether it suits you. You can buy one copy and see whether or not it would be suitable for your students. I mentioned a subject advisor. Irene was there and is still available to you, but there also is a subject advisor specifically supporting the international advanced level, and his name is Tim, and you can you can contact him through exactly the same email address, teachingscience@pearson.com, and there's a phone number there, a UK phone number. And as I mentioned before, really strongly recommend contacting them, if only to sign up to the email update service, which will update you any changes and advancements and developments and advice that come with your specification. Saves you constantly searching the website to check for new changes and new ideas. They will send out email updates on a regular basis when things change. Okay, we've pretty much come to the end of the formal part of this session, quite a long way before the end of time, but we've cracked through this morning. We'll be returning tomorrow for the second part, the second module of the same course, where we'll be looking in more depth at the assessment, the way in which the question papers are structured, different types of question, and supporting students in accessing those. I will stay online for a few minutes after we finish this session in case there are any follow-up questions, but as I said, I will be back tomorrow, and I hope you're able to join us for that session too, and I'll also take questions and answers in tomorrow's session. So if you have no more questions for today, enjoy the rest of your day, and you're welcome to leave the session at this point. If you do have questions, as I say, I'll stay online and give you an opportunity just to pose those questions now before we close the session down. Thank you very much for your engagement this morning. Hopefully look forward to seeing you again tomorrow.